We're starting chapter 21 here. So this is dealing with what's called plate tectonics and, of course, studying the Earth's interior. Really, we're answering the question that was ended at in the last chapter, in chapter 21, about the rock cycle. Why does the rock cycle happen? What exactly causes rocks to change? Um, well, well, not sedimentary rocks. That's not really what I'm talking about. But what causes metamorphic rocks, right? That's really that's really the thing. All right, so this is going to answer this large question, and just let me state it right here and now. It is because the Earth, our planet, is an active world, which means, all right. So here, let's just go to the next slide here. So these are the things we're going to study. The seismic waves tell us about the interior of the Earth. We'll learn about the layers of the Earth. We'll learn about continental drift, and then this idea of plate tectonics, which was greatly ridiculed in the early 20th century, and people did not believe that it was true. And then more and more evidence came along and showed that that's absolutely what's going on. We'll talk about that evidence. All right. So the basic thing here. Let me get to the Earth here. The basic idea here. I'll come back to that slide in just a second. Is that the interior of our Earth is extremely hot. Remember, there's a great deal of pressure. So you have the entire weight of the Earth that's crushing this region right here. We'll get to the why there's two different cores and so forth. But just keep in mind, you have this incredible gravitational pressure, so that's keeping it hot. The other thing that's keeping this hot is there is radioactive substances, really long with really long half-lives, like for example, uranium-238, which we already talked about in chapter 13. So the uranium-238 undergoes decay, and other things, like potassium-40, for example, has a half-life in the billions of years. It's like a little more than a billion years. So anything that has a half-life in the billions of years is still, there's some of that radioactive material is still within the Earth. And so that's causing the Earth to heat as well, the interior of the Earth to heat up as well. All right. So the main thing, and this is what I was talking about at the very beginning, is that our world is an active planet. That is, there is a difference in temperature between a large enough difference. I should state it that way. There's a large enough difference between the Earth's interior and its surface. All right. So the fact that there's a large, and sometimes they call this difference the gradient. Right. There's a large enough gradient, a difference in temperature between the interior of the Earth, the deep interior of the Earth, and its surface, so that causes the Earth to be an active world. And what we're going to do is explore that right now. All right. Just to give you another a quick example, our moon, for example, is a dead world, which means the interior of the moon, and this isn't the moon, of course, but the interior of the moon it's still going to be hot, but it's not hot. It's not a large enough difference in temperature to drive these plate tectonic. The moon doesn't even have plate tectonics going on, for example. All right. Okay. And Mars is very similar. That doesn't seem to, be there's some plate tectonics, but it seems to be really, really minimalized on Mars. But our Earth, it's an active world, and so there's this constant changing that's going on at the crust, and it's caused by this difference in temperature. All right, so let's go back here. When you get earthquakes, so we'll start off and we'll talk about earthquakes. So with earthquakes, they have there are vibrations that are taking place, and those vibrations, some of them anyway, can pass right through the earth, right through the heart of the earth. Some of them will get, as they're passing through the earth, they'll change directions. Here, let's go to this picture right here. So if there's if there's an earthquake, let's say right here, that earthquake, those waves, those seismic waves, which is the same thing as a sound wave, or similar to a sound wave. Those sound waves go go outward in all directions. All right, so they start to, and when they get towards the outer core, something special happens. We'll get into that. And the thing is that we have, since the middle of the 20th century, there are seismic detectors all over the planet. All right, so keep that in mind. As the 20th century moved, the turn of the 20th century is when we first started developing these seismic detectors. And at first it was just to detect earthquakes, but of course we found out a lot more information about the interior of our planet by studying these seismic waves. Right? Okay, so this is, I know I already had this picture up, but so from the interior of the Earth outward, we have, of course, the what's called the inner core. We're going to find out that that's solid iron, a little bit of nickel thrown in there. There's a liquid outer core of the Earth, which is mostly iron again, but there's also nickel as well. Again, the important part about this is it's liquid right here. So for this 2,270 kilometers between the bottom of the mantle and the top of the inner crust, the top of the inner core, that distance right there, that is all liquid. Oh, and by the way, this of course that's the radius of the Earth, right? So the radius of the Earth, it's roughly 6,400 kilometers. All right, so about 4,000 miles, if you wanted to know it in miles. All right, so outside of the outer core is this region called the mantle, right? And so that's we're going to find that we're going to break the mantle up into different parts as well. And then on top of the mantle is, of course, the crust. And there's two major types of crust. There is the continental crust, where of course the continents are, and that's of course, as we talked about before in chapter 20. That's where we find granite, and then the oceanic crust, which is made mostly of basalt. All right, and of course all right. So what was I going to say? Yeah. So that is our kind of a view of a cutaway of our planet. Now, what we're about to get into here is, how do we know this? Where does this information come from? All right. So it's not, in the sciences, of course, you have to have evidence that this is true, right? And so that's we actually had lots of evidence, and we had to interpret this evidence in the beginnings of the 20th century. So that's where we're headed. All right, so let's start off by discussing the types of seismic waves. All right, so there's two general categories of seismic waves: body waves and surface waves. Body waves travel through the interior of the Earth, and surface waves travel, just like its name implies, across the surface of the Earth. For the surface waves, there are what are called Rayleigh waves or Raleigh waves, however you want to say that. And there's also love waves. Okay, so the difference between them is that the so the Rayleigh waves, um, uh, what they do is that they travel up and down like this, it's as though, imagine, you ever see people, with like some ropes, large ropes in each hand, and they lift them up and down, when they're, like, in a workout, um, and then so that would be an example. So the waves are going up and down vertically. So love waves, they're side to side waves. Okay, so they're moving side to side, like if you had a rope on the ground, and it was, it's just sitting there, and you just, pulled the rope side to side, and the wave that would be created, it kind of looks like a snake slithering, on the ground, right? Not up and down. The up and down are the Rayleigh waves, and the side to side are the love waves. And so those travel across the surface. And the surface waves, by the way, cause the most damage. Those, when those occur, when you have really strong, surface waves, that's going to cause tremendous amounts of damage, if you're, during an earthquake. Now for the body waves, we break those into two types, and one's called a P wave, and the other one is called an S wave. All right. So the P waves are, so that they're similar to the way sound waves work. Sound wave is called so A sound wave is called a longitudinal wave. So in other words, what's waving is, you can kind of see it in this picture. Like you look at these lines right here. The Like imagine this. So this is how sound propagates, right? You have, as the sound is created, you compress the airwaves, and then the air stretches apart and compresses and stretches and compresses and stretches. So that's called a longitudinal wave. The wave is moving in the same direction that it's traveling. Right? So that's the idea. The wave is moving in the same direction that it's traveling. That's called a primary wave. And these are by far the fastest waves that are created, in earthquakes. The second fastest is, of course, the secondary wave. These are called P waves. These are called S waves. We're going to find out that P waves can travel through solids and liquids, but S waves can't. S waves can only travel through solid. In fact, sometimes when I think about like an S wave, I always remember, that S waves can only travel through solids. With the S. It doesn't stand for solid, but I always think that, this is the way I remember it personally. Is if it's an S wave, it can travel through solid, and just always remember the P waves can travel through both solids and liquids. All right. So now, what the S waves do. So this is the P waves are what we call longitudinal. That's just a type of wave, and these waves are what they call transverse. So the thing that is waving up. So this is, the wave, the secondary wave, it's waving up and down, and yet the wave is traveling perpendicular to that. So remember, with the primary waves, the thing that's waving, the compression and expansion, is moving also in the same direction. So the wave is moving in the same direction that it's being stretched. The stretching, the up and down motion of the secondary waves, that is perpendicular to the direction that the wave travels. All right, so those are the four basic types of waves that we're going to talk about. So the P waves, S waves, Rayleigh waves, and love waves. All right, and just remember, love waves travel in an S